Let's return now to part 2 of my interview with Dr. Ch.
If you're ready.
I think I am.
Okay. So another question. We've talked a little bit now about what higher order inference is, what higher order is. Why is it important? Why do we care? Why do we need it beyond first order? You've touched on that a little bit, but are there other implications of why we should be working in higher order, or what we can represent maybe beyond just this notion of referring to or quantifying over predicates or classes of predicates? How about statements or other things in logic that we can do that are also important?
I think I've used the main examples I wanted to talk about, which are the induction axiom, right? I could elaborate on this a bit more so imagine a very simple theorem, okay? And I'll keep it about as simple as I can imagine. It's talking about the natural numbers. Let's say you wanted to prove every natural number, n plus 1 is different from n. Seems very true. Why should you have to prove it? Well, if you don't know it yet, you have to prove it, right? And hey, maybe it's not true. You should be skeptical in the beginning, right? Maybe if you go far enough out, n plus 1 will be n, right? Well, of course, you prove it by induction. I would say this is kind of the first example you prove by induction. And in a higher order, you have the induction axiom, right? And you need to instantiate the predicate P in the induction axiom. And the obvious thing to instantiate here is with a P, which says P of n holds if and only if n plus 1 is different from n. You check the base case, which is typically one of the piano axioms. You would check the successor case, which would follow from the induction hypothesis, and maybe another piano axiom stating that basically successor is injective. And fine, then you get, that's how you prove it. Okay. Do this in first order. Well, how do you even ask the question, right? You can certainly write down the conclusion for all n plus 1 is different from n. How do you write down the induction axiom? Well, you can't directly, but you can write down an instance of it, right? You could write down the particular instance with this property, which you already know because you are the one, I just told everyone exactly how to prove it. So you know the P you need to use, so just put that instance in. This is obviously kind of cheating, right? You're telling it exactly which of the instances of the scheme you want it to use. You want, let's say, the theorem prover to use. So it's a different problem then. There's essentially two problems. One is which instance of induction do you need to use? And the other is how do you actually do the mechanics of the proof? And in first order, you really can't say this first part. Like, how do you go from the general induction axiom to the one that you want to use? And that's arguably the hardest part of trying to prove this. It's a very simple example, of course. Any, let's say, non-trivial example becomes pretty unrealistic to expect an automated theorem prover to do.
Well, great example, and actually this sort of ties into, because most of your work is really in the service of mathematics, right? You're in a way not doing higher order proving, and all the work that you did on the Sadillacs prover, which was for many years the leading higher order prover in terms of speed and efficiency, has all been really in service of your trying to prove fundamental things in mathematics. So maybe I could ask a general question, in terms of the applications of higher order proving to mathematics. What has the creation of this field of automated theorem proving, and especially support for higher order reasoning, done for the study of mathematics, as opposed to the sort of traditional way that I think most lay people imagine, is that mathematicians have a pad of paper or a whiteboard or chalkboard and they're scribbling away trying to prove theorems, but now we can do some of these things with software help. How has that changed the practice of mathematics?
Yes, okay, this is a good question, and I could say a couple of things about it. But first, I feel the need for, let's say, academic honesty to say Sadillacs is not efficient. So Cezary Kaliszek has been re-implementing some of the Sadillacs, making it basically 10 to 100 times more efficient.
Oh,
Maybe even more than that.
Wow.
So, yeah. So, Cytoax was a winner for many years, and I'm certainly proud of that work, and especially the theoretical aspect of the work. But it was never really focused on making the code as efficient as probably it should have been. So, okay, but you asked about how does this change mathematicians, the way mathematicians work. And I think the honest answer is not very much at the moment, okay? So I would distinguish between two different things. One is automated theorem proving and the other is interactive theorem proving, right? In terms of automated theorem proving, there have been some successes in some pretty niche areas of mathematics. The really famous one early on, it was in the 90s.
That's
Counts as
ancient
early
history
on.
now for this technology.
Yeah. So there's Bill McCoon, who was one of the pioneers of first order automated theorem proving, who proved the Robbins conjecture using an automated theorem proving.
Yeah, that's always the example that everybody in theorem proving trots out to make the point of how important and useful this was, at least to mathematicians.
Yeah, so this resolved an open problem in mathematics. So
Yeah.
that's pretty impressive. Yeah. I'm not sure how many mathematicians cared about that open problem, but nevertheless, it was certainly a success and worth remembering. A more recent thing that happened was the AIM conjecture, which is a conjecture in algebra about certain kinds of loops. In case people don't know, a loop is a kind of algebraic structure. Loosely speaking, it's a group that may not be associative. Okay? So you drop the associativity axiom. And I won't say what an AIM loop is, but okay. There was a conjecture about how strange can AIM loops be. And the conjecture is not too strange. Okay? And the two main people I associate with this problem are Bob Veroff and Michael Kenyon, where Veroff is more on the computer science ATP side, and Kenyon is more on the math side. He's the mathematician working on it. And I think Bob probably has a reasonable math background too. But
I think you'd have to understand the problem.
but Kenyon is the one who works in the math department. So it got resolved, I think, last year, and this is after at least a decade of them working on it, maybe more. And a lot of that work was done with an automated theorem prover, Prover 9, which was another theorem prover due to Bill McCoon. And loosely, I'll describe it as I understand it from the outside. I've worked with them a bit, but this is mainly their work. Veroff would get some conjectures in first order from Michael Kenyon, and he would try to get Prover 9 to prove those, and when it could, fine, and when it couldn't, you would try to get some, let's say, weaker results and learn from that. So there was a lot of back and forth where Prover 9 would generate lots and lots of information, which would probably be meaningless to most people, but Kenyon he knew enough about the problem that he could scan through this and see, oh, that's an interesting property. So it would change his way of seeing the problem, and it would lead to new conjectures you could send to Prover 9. And I think they got a long way doing this. So I think it's fair to say that, in this case, the automated theorem prover helped to lead to the solution. I think it's also fair to say that the solution ultimately came from Kenyon, the human working on it. So, but it's interesting that it helped.
But it sounds like, in a way, the prover is acting like a student, a graduate student, where the professor can say, please try to prove this interesting thing that I think will contribute to the overall solution. So instead of the real mastermind spending a lot of time proving something that it should be possible for maybe a less experienced mathematician to go ahead and prove, you could just send it off to this assistant. So the idea of, again, computers being our assistants or our helpers really is sort of a valuable metaphor.
Yes, I think that's true, but if a graduate student came to me with 10,000 equations, I'm not sure I would scan through it looking for the needle in the haystack. But in terms of interactive theorem proving, I think probably more mathematicians have been involved with this than automated theorem proving. And there was a famous example recently, I guess not that recent now, but Fleischbeck the Hell's proof of the Kepler conjecture, which was formalized in whole light. Whole light is an interactive theorem prover. Of course, there's plenty of automation in it, but it's not an automated theorem prover. It's a different focus, where basically the person who knows the proof is trying to convince the theorem prover, hey, this is the proof, okay? Basically, help it build the proof. It's much more common in terms of someone trying to verify some mathematical proof. Also, I know that, well, first of all, lots of math has been formalized in lots of different systems. Mizar, Koch, and Isabel, and probably some that I'm forgetting, okay? There's recently been work, there's something called the Xena project that got a lot of traction. And this is Kevin Buzzard working out of the UK. He's using Lean, which is a relatively new theorem prover. It's based on a lot of the same ideas as Koch. It's basically Microsoft's version of Koch. Koch is a French theorem prover that goes back to the 1980s. So that's the way I see it impacting mathematicians at the moment.
And I seem to remember in the popular press discussion of some very long theorems that are proofs that a human mathematician had come up with. Correct me if I'm wrong, I think it might have been Fermat's last theorem, where there was then because the proof was so long that they needed a way to determine whether in fact that proof was true. And so at least portions of it, I think, were validated with an automated theorem prover or maybe an interactive theorem prover.
Yes, I think you're thinking about the Kepler conjecture. So the Kepler conjecture was an open problem for centuries. I would have to look when it obviously came from Kepler.
Yeah.
And actually, it's on, I think, Kepler was based out of Prague, which is a very interesting city.
Yeah.
Stating very carefully. And so, yes, maybe that's all I say about that. So that's an interesting example where, Hells did this proof. It's by a mixture of work by hand and computer algebra systems, the way I remember the story, and submitted the proof to be published in some journal. I've forgotten the journal. But the reviewers worked on it, I think, for 2 or 3 years before deciding we can publish it, but only with a disclaimer that we can't really verify it. And so this led to a long-term project to formalize this proof in an interactive theorem prover. And he chose whole light for this. This is John Harrison's system, and which has a number of things about the real numbers in it, which I think, and a lot of support for the real numbers, I think is part of why it was chosen. And this was done it's finished now, my understanding. It's certainly, there's been a paper published about it being finished. And what's the important thing there? So you can say in that case it was formally verified in a theorem prover. I have no idea if this means mathematicians are more likely to believe it now, right? So certainly it makes me more likely to believe it. Yeah. But you have, in some ways, the same problem that you say, well, I don't believe the computer. Yeah. If I didn't go through the proof myself, then I still don't believe it, whether it's computer algebra saying this is the result of doing this computation, or a theorem prover saying I completely checked a formal proof in a logic you may not understand, right? With axioms you've never gone through. Right. You have a lot of the same problems. So it's certainly a success story, but I don't know if it's changed the way mathematicians view things. I certainly think it will in the long term. Of course, there's this famous quote by some physicist that science progresses one funeral at a time. Right? So I think it's, among young people, it's part of why I brought up the Xena project. It's becoming much more accepted to use interactive theorem provers. Yeah, I think they grow up with an understanding of it now.
Yeah, it's hard for a field to change, but at the very least, I would think you could treat the computer as one more set of eyes, right? Everything has to be subject to verification and validation over time, but it never hurts to have another person or another system that has some degree of confidence behind it, checking what we do. And I guess I also I was thinking as you were mentioning this, having to grade some student papers recently and fretting over how much time it took. And imagine if rather than a paper, you were tasked with checking a journal article, where just checking the math in the journal article was going to take you 2 to 3 years and still not be done.
Yes.
really puts some of these day-to-day prosaic things about checking tests into perspective, doesn't it?
Yes, it does. And imagine how often a reviewer says, well, it's probably correct, and just goes on with their day.
Yeah.
Right? So it's amazing that there aren't more examples than there are of wrong mathematics being published.
Yeah.
Right? So mathematicians are pretty good at spotting this stuff, but surprisingly good, I'd say. I would expect there to be more false positives, I guess.
Yeah, because proofs are problems. The problems that remain unsolved are getting harder, and the proofs of them are getting much harder and much longer and more detailed. And so I would think this problem is going to come up more, and the one way to address it is going to be through automation.
Well, yes, there's sort of two different kinds of automation. There's proof checking, which doesn't really require search, right? But in order to check the proof, you have to write it out in a very detailed format. And typically you need at least some support, some automated support to generate this. Now, that's essentially what an interactive theorem prover is doing. You are using the support given to you by this interactive theorem prover to build a very detailed proof, which you are not looking at, but the prover can check it's correct, right? So,
And that seems to tie in very well to a colleague of ours who's appeared on this channel, Joseph Urban, who has been very eager to do work in auto-formalization, or having the computer try to create these formalizations of mathematics automatically, so that a human being doesn't have to laboriously go through a human proof and create some formalization that could then be subject to the automation.
yes, there's really two very different problems there. One is, how do you write down the thing you think you are trying to say, right? And obviously, humans usually do it either on a blackboard or on paper or in LaTeX, right?
Yeah.
This is semi-formal at best, right? So how do you convert it into something a theorem prover can even say, yes, this is a proposition, not whether or not it's true, right? And the second thing is, how do you follow the line of reasoning in a human proof, right? Which is really the second level. And yes, so it would be very helpful if there were something that could read a math paper and then turn it into something a theorem prover could check. But I don't think we're there yet. So.
Yeah, just even thinking about how one might do that, LaTeX or writings on a chalkboard is a visual presentation for humans. And so how do you get the machine to understand even something as simple as, say, division, right? So this is visually above that, therefore you interpret it as division. Just getting that sort of visual presentation converted into a logical presentation has challenges, even the simplest case that I can think of as a layman.
Oh, yes. Yeah. Even simpler cases are hard. So, there was a success story over 50 years ago now, clearly in the proof checking and formalization camp, where there was a very simple book, math book, written by Landau. He was not a simple mathematician, but he wrote a very simple book.
Which is great.
Yeah. It basically builds up the real numbers and complex numbers, starting from the natural numbers.
Let's pause here and we'll return for part 3 of my interview with Dr. Chad Brown.